Nuclear magnetic resonance. We are going to be talking about two different NMR techniques. One is going to be proton, the other one is carbon. So in this one, I'm going to introduce you to the proton NMR. There will be two presentations on the proton NMR, this one and there's another one. Okay, so not everything is completed in this one. NMR is one of the most useful techniques for structure determination in organic chemistry. It's very powerful. It gives an absolute structure, and organic chemists generally swear by it. If you've taken an NMR, you don't need anything else. We've talked about all the different techniques by now. IR will help you determine the functional group. UV-Vis will help you determine a little bit about conjugation in there, and then mass spec gives you the mass, but none of those techniques will give you the actual organic structure, how carbon is bonded to which carbon and how many hydrogens does it have. But NMR actually does that for us. Okay, it gives you the exact structure. So organic chemists really find this the most useful tool for determining the structure. There are a few isotopes that we study for NMR: H1, C13, nitrogen 15, F19, and phosphorus 31. These are the isotopes that are studied for NMR. Since all organic compounds are made up of hydrocarbons, really the hydrogen and carbon 13 NMR, they become the most useful tools. For nitrogen, phosphorus, and fluorine, things are a little bit different, and as we go on, I'll talk about how the instrument works also. But these three are not studied as much, and their instrument is slightly different as well. But hydrogen and carbon, they can be studied by using the same instrument. One thing I want you to note over here is that hydrogen 1, that is the most abundant isotope of hydrogen. However, carbon 13 is not the most abundant isotope. Carbon 12 is the most abundant isotope for carbon, not carbon 13. But for NMR, you study carbon 13 and not carbon 12. So we will talk about why we do that when we get to carbon 13 NMR. In this presentation, I have only proton NMR for you. And that's also the case here for nitrogen, okay? And so it has to do with characteristics of the nuclei, all right? And that's why we study these particular isotopes and not all of them, okay? So it's not possible to study all of them. So the nuclear spin gives you a little bit of an idea of why we do this, but then things will become clearer as we go on also. So a nucleus with an odd number of mass will have a nuclear spin. Okay, now remember, inside the nucleus you have two particles, the proton and the neutron. The proton also has its own spinning, okay, going on. So just like the electron, which has a magnetic spin of plus half and minus half, the proton also has the same kind of thing going on, all right? And so once you have a proton that is spinning, it will also generate a magnetic field, okay, by itself. So this is the magnetic field that we end up studying in NMR. So when you have odd numbers like 1, 13, 15, that means that you actually have an odd number in the nucleus. And so that is what helps to generate the magnetic field, and that is actually how we study the NMR. Okay, and so you need to have an odd number of mass number, okay, in order to study that nuclei in the NMR. So what happens to protons is if you provide them a magnetic field, they will actually align with the magnetic field or against the magnetic field, okay? And so it is shown a little bit better in this figure over here, okay? So here are your bunch of nuclei without any field, all random and haphazard, facing whichever way. But as soon as you provide a magnetic field, okay, to that compound, then suddenly you have two different kind of spins. Okay, one is the lower spin, in which case your nuclei is going to be aligned with the magnetic field, and the beta spin, in which case the nuclei is opposite the magnetic field. The opposite the magnetic field, of course, is the higher energy. The one with the magnetic field is the lower one in energy. So then what happens is in NMR, when you give energy to the alpha spin to go to the beta spin, that energy is what is measured, okay, in the NMR. And that is given by what we call the radio frequency. And if you remember radio frequency from the electromagnetic spectrum, that was the lowest energy in the spectrum, okay, the radio frequency. So that is what is given in order to flip, okay, a nuclei from with the magnetic spin to the opposite, okay, of the magnetic field, okay, or with the magnetic field to the opposite of the magnetic field. So that's what is measured in the NMR, all right? So let's look at an NMR spectrum and then see what we are looking at, okay, in a spectrum. This is what an NMR spectrum might look like, and depending on the instrument that you have, the signals may be like this or a little bit different. But anyhow, we'll talk about the scale also in a little bit, okay, which over here is called ppm, which is parts per million. But the scale really actually is in hertz, okay? Remember I mentioned to you in the previous slide that the energy that we use to flip protons is coming from radio frequency. So the radio frequency is really what we are measuring over here. So anyhow, I'll talk about ppm in just a minute. But this is what an NMR would look like, all right? So the first thing we look for is the number of signals, okay, that we have in an NMR. So the number of signals will tell us how many different kinds of protons we have. So in this compound, you can see that these two protons are different from this proton because the green one is attached to a carbon with 2 bromines, and the red ones or the pink ones are attached to a carbon with only 1 bromine. So there are two different kinds of protons. Now these two, the pink ones, they're both the same because they're in the same environment, because this single bond can be rotated. So at any given time, these two protons will be in the same environment. So that will give us the number of signals that you see, okay? So which will be 2 in this case. The next thing is we look for the location of the signal, which is also called the chemical shift, okay? And the location of the signal, that is when the scale is useful, okay? So in this case, we have a signal at about 4.1 and then at about 5.7. Okay, so we have two chemical shifts over here, and right now I'm not going to talk about why these protons are coming here and why the green one is coming on this side, okay, which we will talk about in the next few slides. But that's what we are looking for. That is called the chemical shift. The third thing we look for is we look for integration, okay, which is called the intensity also of the peak. So the integration is the height of the peak, and in the height of the peak we're actually measuring the area under the peak. The area under the peak will tell us how many protons you have. Now sometimes when you look at these signals, they're not exactly to scale. So in this case also they're not exactly to scale, but you can see that they're actually in a ratio of about 1:2. So which tells you that you have one proton, or whatever number of protons you have under this signal is half of what you have under this signal. So it doesn't tell you that you have one proton. You have to determine that, but it tells you at least the ratio of the signals. So this is 1:2. So that is called integration. And then finally, there is something called the signal splitting, which is also called coupling. And coupling shows the number of protons on adjacent carbons. Okay, so here if you have carbon and you have protons on each of them, then each of them will look at each other and they will split, okay, into different numbers. And the splitting we will talk about in the next presentation, not in this one. In this, I'll just focus on the number of signals and the location of signals. So that splitting, the coupling as we call it, is really very, very key in giving you what the structure of the compound will be, because it tells you exactly which hydrogen is next to which hydrogen. Okay, so looking at all of the four things that we have just mentioned here, what else would you need, okay, in order to determine the structure of a compound? You can find out the different number of protons, whether something is shielded or deshielded, how many protons you have, and then how they're attached to each of the carbons. So that is like perfect and ultimate information that you can get, okay, from any kind of an instrument. So here's a schematic of what an NMR would look like. Any instrument that you have for NMR will have the same kind of things in there. What size it would be, and that all would be different. Okay, so anyhow, you would have a huge magnet, and the huge magnet is required because you need to generate that magnetic field, okay, in order to view the protons. You have to have the sample tube, of course, all right, which is going inside the magnetic field. These wires that you see are the ones that provide the radio frequency, and remember the radio frequency is required to flip the nuclei from with the alignment with the magnetic field to opposite of the magnetic field, the alpha beta transition that we talked about. That flipping is provided by the radio frequency. So that's what this is. The NMR tube sample actually goes right inside the magnet. It kind of disappears inside the magnet, and there it spins, okay, inside the magnet. The spinning will cause then all the nuclei to be exposed equally to the magnet. So that's what's going on over here in the actual instrument. And then you have the detector. The detector is detecting when the nuclei is actually in resonance with the radio frequency that we have provided. Okay, and so once that is in resonance, which means the energy flip, okay, that it took, that flip is being measured by a detector. So you can imagine how good the detector has to be in order to measure that very, very tiny energy flip that we're talking about. And then the detector will translate that into an NMR spectrum like you saw in the previous slide. So that's the recorder then, all right? And so this is really what an NMR looks like. The link over here, you may be able to see this in the PDF, or you can just type in NMR spectrophotometer in Google and then check out all the instruments. Okay, I have a couple pictures here for you. The one on the left is from a national lab, and of course national labs have oodles of money, and so they will have the best NMR possible. The quality of the NMR depends on two things, okay, the magnet and the radio frequency. Okay, so if you have a really good magnet, you have to have good frequency also. If you have a really good magnet but not a good radio frequency, what's the point? Okay, it's like trying to drive a Lamborghini on a dirt road. That's not going to work. Okay, so for a good road, you need a good car, all right? Or for a good car, you need a good road. So that's kind of the thing that happens with the NMR. Okay, you need to have a good magnet and a good radio frequency. So the radio frequency can be from 200 megahertz to about 1000 megahertz. So as you get to the 1000 megahertz, you're really getting into very good energy flipping going on. Okay, so once you have very good energy flipping going on, then you get a very good spectrum. You can detect a lot more in the 1000 megahertz rather than the 200 megahertz. So the instrument here on the left hand side in the national lab, this is probably an 800 or a 1000 megahertz instrument. Okay, so you need a huge magnet also in order for the sample then, okay, to be able to show that flip that's going on, that will need that radio frequency. The NMR on the right hand side is probably a 400 or a 500 NMR, and this one you can see is, you know, it doesn't need stairs for you to climb up, but usually you will need some sort of a stool or something to get up to the NMR, because sometimes the sample is placed from the top. You can see this gentleman over here, and he's placing the sample from the top, and sometimes from the bottom. Okay, it depends on the instrument. So there are many companies that make NMR instruments, Joule, Varian, and so depending on what kind of a company your instrument is from, your sample can go from the top or from the bottom. So in any case, this is what the instrument looks like. The magnet is encased in these steel containers. And one other thing that I should mention is that the higher the frequency, the higher strength of the magnet that you need, as I just said. So which means that these magnets, you know, get really very hot, okay, as the instrument is working. So which means that they need to be cooled down. So these steel casings also provide for a place for insulation. So you have to provide liquid nitrogen, okay, in order to cool the magnet down. So really the instruments require a good amount of maintenance, okay, in order for them to work. Most of the NMR instruments would be found in the basements of most of the departments or labs, so that, you know, you're not affected by anything else. They will be isolated because it's a magnet, and you should not have your credit cards there. You should not be wearing a pacemaker when you go to the instrument. So all of these things, because all of these things will be affected by the very strong magnet. Okay, so when you work with NMR, you really have to be trained properly in order to work with it. But anyhow, it's a really cool instrument. So making the sample for NMR is also a very different kind of a thing. Previously, we didn't really talk so much about sample prep because it was very easy. IR, you use a neat sample. In UV-Vis, you just dissolve the sample. And in mass spec, you bombard your sample. Okay, so you need a neat sample. You don't need to dissolve it in anything. For NMR, you need to have a very specific kind of sample design. Okay, so first of all, you need an NMR tube. This is what an NMR tube looks like. It's like a pencil, very, very slim. And you fill the sample up half the way. Okay, you have to dissolve your sample in any solvent that is NMR inactive. Because remember, when you're looking at protons, almost all solvents have protons, all right? So for example, even if you take something like chloroform, which CHCl3, you have one proton in there. And if you're using a solvent which has one proton, it means you have so many molecules of chloroform in there, which means that by the time you run your sample, the only thing you will see is chloroform. You will not see your sample because the molecules of chloroform are way more than your sample. So it will overwhelm your sample. So which means you need to have a solvent which does not have any protons in it. So what happens then is that most of the solvents that we use for NMR have to be deuterium based. Deuterium is heavy hydrogen, okay, which is an NMR inactive isotope of hydrogen. Hydrogen proton, which is the one that we detect in NMR, is H1. Deuterium is H2. And so deuterium H2, because now it is paired, now it's not going to be, the nucleus is paired now, and so it will be NMR inactive. So you can use any of these solvents, in which case the hydrogen has been replaced by a deuterium, then you can use them. So for example, chloroform becomes CdCl3, which is deuterated chloroform. Okay, water becomes D2O, which is called heavy water. And you can also use methanol. You have to switch around all these protons. So you have to use deuterated solvents in order to make your sample. So, but the solubility doesn't change. Okay, the properties of the solvent doesn't change that much. So the solubility is the same. So if your sample dissolved in chloroform, it will still dissolve in chloroform. If it dissolved in water, it will still dissolve in water, whether it's deuterated or not. So once you dissolve your sample, you will go ahead and put that in the NMR tube halfway through. You try and make your sample as concentrated as possible, because the more nuclei you have of your sample, the better NMR spectrum you will get. Okay, so you try to make a nice concentrated sample. In some cases, you also need to use what is called TMS, tetramethylsilane. Tetramethylsilane is what we call a reference solution. And so you need to put a drop of this reference in your sample when you make it. And what it does, it gives you a starting point. Okay, and I will explain this more in the class also. But TMS absorbs more in the highly shielded region, and so whenever you see a TMS signal, that is considered to be the zero signal. So at least you have a starting point. Otherwise, sometimes we don't know how to reference that scale. Okay, the TMS, the ppm scale that you see at the bottom, you have to generate that scale yourself. Okay, and so in order to know how to start and where to start the scaling, TMS is used very frequently for that. So wherever you see the TMS signal, which will come as one signal, okay, that will be defined as zero. Okay, and so then everything else will be to the left of the TMS signal, okay, or to the downfield of that. So that is how you make your sample. Now, depending on the sample that you're using, you may or you may not use TMS. It depends, up to you. I never used TMS during my entire NMR studies. Okay, so it depends on what kind of sample you're using, and maybe you need to see something around zero. Okay, and so it depends, but most of the times you can use TMS. So this is how you make your sample. Once you have taken the NMR, you can recover your sample right back. Okay, all you have to do is evaporate the solvent, and then you can get your sample back. So that's the nice thing about NMR, at least, is you don't lose your sample. Okay, in UV-Vis also you don't lose your sample, but IR and mass spec you tend to lose your sample sometimes. And so in NMR you don't lose your sample. So that's one nice thing. So anyhow, this is how you make your sample for NMR. And this is the tube that actually goes inside the instrument. So I showed you the graph before also, and this is really what the graph would look like. And here is the magnetic field. The magnetic field strength, okay, over here is just given as strength, but really we study it in ppm. We don't even study it in hertz, okay? So here it is given in magnetic strength, which means that here you have a very high magnetic strength, and remember this is going to be the TMS signal because this is the rightmost signal. So this is TMS, and then everything else will be scaled according to that. These two signals that you see over here tells you that you have two different kinds of protons. The fact that they're not splitting, okay, we'll talk about that later, okay, as to why they're coming as just singles over here. Then the fact that this one is coming on the right hand side of this one, so which means that the blue signal is coming on the right hand side and the pink one or the red one is coming on the left hand side, tells you which one is shielded and which one is deshielded. So this one is less shielded, okay, the one that is attached to oxygen is less shielded, and we call it deshielded. The blue ones are what we call shielded, okay? This region is called the upfield region. This is called the downfield region. So you have all of these terms to keep in your mind, okay? When you're looking at an NMR, that you have the TMS signal, you have the upfield region, you have the downfield region. Then you have the protons that are deshielded and the protons that are shielded, okay? So the shielded protons will come in the upfield region, okay, over here. I was talking to you about the intensity before, the integration, and here the ratio of the protons is 1:4. But look at this. This intensity over here is not exactly 1:4. It looks like 1:2. So which means that you really have to do proper integration. Okay, you cannot look at the size of the peak and determine the number of protons that would be under that peak. Okay, so we will talk about integration later on also. Anyhow, this is what an NMR spectrum would look like. So let's talk about chemical shift 1 first, okay? Because chemical shift is really how you see the signal, all right? And that is the lower scale that we talked about, all right? So the chemical shift that we have is, first of all, is measured in parts per million, okay? Parts per million means it's a ratio. Parts per million, 1 in a million, all right? It is the ratio of the shift of TMS to the frequency of the instrument. Okay, so since it's a ratio, parts per million is a ratio. So what you look for in there is you look for the shift, the downfield shift from TMS. Remember, TMS is 0. And you look at this shift in hertz. Okay, remember the instrument is in megahertz, whether it's 200 megahertz or whether it's going to be 600 megahertz or 1000 megahertz. All right. And when you say mega, mega stands for 10 to the power of 6, which is really a million, okay? And hence 1 hertz in a million is parts per million. That's how we get the parts per million scale, okay, over here. So if you have a 0 hertz over here, then all your signals are coming in different hertz, okay, on the left hand side. Once you take the ratio of those, okay, according to the TMS, you can get the scale from 0 to about 10. And technically, the scale goes to about 12, actually. All right. And so no matter what instrument you are dealing with, okay, which means whether you're using with a 200 megahertz machine or a 1000 megahertz machine, your ratio is going to be the same because the shift that is downfield from TMS is going to be the same. It'll just be a different number, but then your megahertz is also going to be different. So by the time you calculate the ratio, whatever signal that was coming at 2 ppm will also be at 2 ppm, whether you use a 60 megahertz machine or a 300 megahertz machine, because your signal is actually a ratio. And this is something that the machine calculates itself. You don't have to do the calculation. The delta scale, as we call it, okay, which is a ppm scale, the delta scale, that is all calculated by the machine. So you hardly have to work with hertz scale. You work with ppm scale, okay, for most part. But in any case, the most important thing here is that your scale is in ppm. It's in a ratio, okay, and that's what the blue scale here is for. We will be talking about hertz, yes, a little bit, okay, but not in the scale method, all right? But anyhow, that's what the chemical shift scale is. Now let's talk a little bit about the shielding and the deshielding. I mentioned to you that the shielding is on the left-hand side. The shielding is on the right-hand side and the deshielding goes on the left-hand side of the NMR spectrum. Remember, the TMS is on this side, okay, on the right-hand side of the spectrum. So what happens, okay, with the deshielding that you have, it means that the nucleus is exposed more to the magnetic field. With the shielding, then you have the nuclei that are actually shielded, okay, so they're not so much exposed to the magnetic field, which means it takes a lot more of the magnetic field. If you remember one of the older scales that I showed you, there was the increasing magnetic field was towards the right hand side, okay, so which means that the highly shielded ones will be in the higher magnetic field, okay, so which means that you will need a lot more magnetic field, okay, in order to see them. So how does this work? All right, so here you have these protons, okay, this is methane, and all of these protons are alike, okay, right now they're all the same, and they will come, say, at a chemical shift of 0.2 ppm, okay. If you add one chlorine to this, now it will change everything about the carbon here. Why? Because chlorine is electronegative. If it is electronegative, it's going to pull electrons towards itself. If it pulls electrons towards itself, these hydrogens now, they become exposed to the magnetic field. If they become exposed to the magnetic field, then they will be what we call deshielded. Okay, so they will come on the left-hand side. And you can see the chemical shift over here. It's about a difference of 2.8 ppm, which is a lot, really, just by one chlorine. You add two chlorines to that, and then you will see another jump of 2.3 ppm, and now you have more deshielding going on to 5.3. And then another chlorine, which means now you have one hydrogen. The poor hydrogen is being exposed so much to the magnetic field, it comes at 7.2 ppm. Okay, and so this is what shielding and deshielding means. When we say something is shielded, it means it's shielded by electrons. When we say something is deshielded, it means that there is an electronegative element there, okay, somewhere. So the electronegative element will cause an increase in the chemical shift, all right, and cause deshielding. So as the electronegativity increases, you will see the protons shifting from the right-hand side onto the left-hand side. Okay, that's how it works. Here are some typical chemical shifts. Now, these things you cannot memorize really. This is something that comes from practice. There are some things that are very key in identifying an NMR spectrum, but just like you saw in the previous slide, that adding one chlorine can change the chemical shift so much, there is no point in memorizing any of these numbers, okay? Because if you add a chlorine or a bromine or a fluorine to a compound, it will change the chemical shift, all right? But these are some of the typical values where you can actually find these protons. And so in some cases, you can get a general idea, okay, if you have a very typical kind of a compound with no major electronegative elements in there. So for example, all the alkane protons will come around 0.9. They're really shielded because they're all alkanes, which means they have carbons in them and hydrogens in them, and it's all electrons. And so they are shielding the nucleus, and therefore they will come at the shielded region, okay, which is the right-hand side of the region. Alkanes with the CH2, okay, will now start getting shifted, okay, to the left-hand side, to the deshielding region. Then alkane with a CH, even more deshielded. Now you can't really tell the difference too much between alkane, the CH2 and the CH, okay? I wouldn't use this table to figure out the difference between a CH2 and a CH, okay? And I will not tell you to do that either. By the time you get to something like a methyl ketone like this, then you know that because of this carbonyl, it's going to be deshielded, all right? So it will come around 2.1. So here it went from CH3 as an alkane, 0.9 to 2.1. An alkyne proton is very deshielded, it goes to 2.5, okay? An alkene is even more deshielded, okay? It comes at 5 to 6 ppm. We will talk about these two in the next few slides, okay? Coming up soon. If you have a halogen or an oxygen and electronegative elements, then you can see a shift of about 2 to 3 ppm, as we talked about in the previous slide also. Then going along with the aromatic, Aromatic protons come at 7.2, and really this is a very kind of a key thing in determining if you have aromatic protons or not. No matter what you have on your aromatic ring, they will come around 7.2, 7.6. So it's really very easy to tell that you have benzene rings in there. Okay, and so that's what the 7.2 is for aromatic protons. These protons are what are attached to the aromatic ring, okay, which comes at 2.3. So this CH3 is almost as bad as if it was attached to an electronegative element, okay, and so which means that it is little deshielded, and the deshielding is going on because of the aromatic ring. Then we have the aldehyde. The aldehyde is definitely going to be deshielded because of the oxygen in there. So this hydrogen is directly attached to the carbon with the oxygen. So this comes at about 9 to 10, and then the carboxylic acid is from 10 to 12. The aromatic, the aldehyde, and the acid, these are very characteristic chemical shifts, okay, that you should keep in mind, because if you see anything around 7.2 or 9 or 10, then you know very clearly that you have aromatic or aldehyde or acid, okay. All right, now the alcohol peak is variable, okay, it comes from 2 to 5, which means you really don't know, okay. You have to do some other studies in order to figure out if you have an alcohol, if you just have one hydrogen in there, so you really have to work on that, okay, a little bit. And the same thing goes for the nitrogen hydrogens also, okay, they are variable, so depending on what kind of a compound you have. But there are ways that you can study the OH and the NH2, the alcohol and the amines, okay, there is a way to do this, and I will talk about that a little later. Okay, so the equivalent and the non-equivalent protons. This has to do with how many signals you see, okay, in any kind of a compound. So if you have equivalent protons, then you will see less number of signals. If you have non-equivalent protons, you will see more signals, because non-equivalent means that you have different kinds of protons in there. So for examples, you look at this compound, okay, over here, which is very simple, butane, okay. So when you look at this compound, you can see that you have two different kinds of protons, all right, in here. You have the CH3 and you have this CH3, and then you have the CH2 and the CH2. So again, going back to our symmetrical days, okay, if you slice this in the middle, you can fold this compound on itself. And once you can fold it on itself, then you know you have symmetry in there. And once there is symmetry in there, it means that these two protons are going to be the same, okay, on these two carbons. Now remember, in the proton NMR, you're not seeing carbons. You're only looking at hydrogen signals. You're not looking at carbons. You're not looking at halogens, nothing, okay, just hydrogens. Okay, so if they are the same, then they're called equivalent, okay, hydrogens. And one of the ways to determine whether you have equivalent hydrogens or not is by replacing a hydrogen with a halogen, okay. And this is hypothetical. This is not something that you go in the lab and do. You can do this hypothetically. So if you replace one of the hydrogens over here, the blue ones, the CH3, with a halogen, then only one substitution product is possible. Why? Because if you have the halogen here or here, it's the same thing, all right? And therefore, it tells you that you have these three hydrogens that are going to be what we call homotopic, okay, which means they're the same, all right? So that is how you kind of determine, okay, in some cases, whether you're going to have equivalent or non-equivalent protons. I go with the symmetry, okay. I look for the environment of a molecule, okay, and I see if you have the same environment or a different environment, okay, in any kind of a molecule, and that tells me whether I have equivalent or non-equivalent protons. So here, for example, if I replace the green protons and the blue protons with halogen, then I will get two different compounds, okay, which is what tells me that I have heterotopic hydrogens, okay, and so I have two different kinds. So I usually don't do this for my compounds. I usually work with symmetry and I look for the environment, okay, so I'll explain that also. Okay, so let's look at some of the examples for equivalent and non-equivalent protons. So for example, if you have a structure like this, which is acetic acid, then how many equivalent or non-equivalent protons you have? if you can see from here without drawing the structures, and that is fine, but if you need to draw the structure out, you should initially at least. Maybe later you'll get comfortable. Okay, so you can see that these three hydrogens are going to be the same, and this hydrogen is the same. All right, well, the same, there's only one of them. So these two are in different environments, so which means that you really have two different hydrogens, okay, in this case. So which means that in the NMR you will see two signals. Here's another one. So C6H5 is of course a phenyl group. Then you have a CH and CH3, two of them. That means an isopropyl group. So if you can see the structure like this is great. If you cannot, then draw it out. So let me give you a second to get an answer. Okay, so here's your benzene ring. Here's the CH and here are the CH3s. So these protons are going to be the same because this is benzene protons. These two are going to be the same because this bond can rotate, and then this hydrogen is different. Okay, and so you have 1, 2, 3 signals. Okay, in this case. So we have 3 different hydrogens. So you see 3 different signals in the NMR. Okay, one more. So here's a compound. Now when you see something like this, in this case, it would be the best if you draw the structure, because then you can clearly see what the protons will be like, and you don't have to draw all the hydrogens out if you don't want to. Okay, at least draw a line structure so you can clearly see what the bonding is like. Okay, so once you know this, then this CH3 and this CH3 are alike. There is a hydrogen over here. Don't forget, that's the hydrogen. So 1, 2, 3, 4. Okay, so you'll have 4 signals for this compound. For this ether, this is isopropyl and this is ethyl. So ethyl isopropyl ether, you'll have 4 signals for it. Now, just because you have a CH3 over here and CH3s over here does not mean they're going to be the same. Okay, these CH3s are separated by a CH, whereas these CH3s are separated by a CH2. Okay, so you will see 3 signals. Maybe they are close to each other, or excuse me, you will see 2 different CH3s. They may be close to each other, but they're not going to be the same. They're not what we call equivalent, and we don't call them equivalent, again, remember, because if you switch them with a halogen, you will get a different compound. Okay, that is why they're not considered to be equivalent. These two CH3s are considered to be equivalent, okay, because switching one of the hydrogens with a chlorine or any other halogen will give you the same compound, but not this one, okay. And so these 3 CH3s will give you 2 signals, one for this and one for that, and so there you have 4 different hydrogens in this case. All right, so that is how you will have to do for me also, is I'll give you a structure and then you figure out how many equivalent or non-equivalent protons you have, which means how many signals will you see. Okay, so then let's talk a little bit about shielding. We talked about it before also. So magnetic shielding is when you have protons that are not exposed so much to the magnetic field. Okay, so what happens is that the protons, if they're surrounded by electrons, then they are shielded, okay, from the external magnetic field. So those are the protons that come on the right hand side. Okay, the deshielded protons will come on the left hand side. Remember that always. Okay, so that's kind of how it goes for magnetic shielding and deshielding. So luckily for us, if you have shielding or deshielding going on, then you have protons that are at different energy levels. And so which means that their alignment is at different energy levels. And that's really very helpful in determining the structure, okay, of a compound. So anyhow, the magnetic field strength must be increased for a shielded proton to flip at the same frequency. Okay, so for a shielded proton, meaning if the proton is over here, if it's shielded, then you need to have more of the magnetic strength. And if you remember, the magnetic strength also goes towards the right. Okay, so you'll have more magnetic strength, and the frequency is the same frequency because this frequency is 300 megahertz or 600 megahertz, all right? But the magnetic strength will be increased, okay, in that case for a shielded proton to flip. So that's kind of how magnetic shielding works. If you don't understand this part too much, don't worry about it. Just remember how the electronegativity works, okay? If you have electronegative elements in there, then the protons will be deshielded. If you have a lot more electrons in there, then they'll be shielded. So for example, in this case, these 3 protons here in methanol, they're going to be shielded because of the carbon, whereas this hydrogen is going to be deshielded because of the oxygen. Okay, very simple, straightforward. So first of all, you have 2 signals in the compound. In methanol, you'll have 2 signals, and then this hydrogen will come more of downfield, whereas these CH3s will come more at an upfield region. Okay, that's how it works. Regarding the aromatic protons, these are a little bit different because remember they came at 7 to 8 ppm, and the aromatic protons are a little bit different because of how the pi electrons are existing in there. Remember that there's a whole lot of conjugation going on, and so what happens is that the benzene ring will align itself like this, okay, in the magnetic field. And therefore, there's a lot of deshielding going on for these protons because now they are exposed to the magnetic field. All right. So because of this reason, the aromatic protons will come at a deshielded region. The vinyl protons, which really is about the double bond. Okay, the double bond protons are also the same way. They're also deshielded, which means that this is how the double bond is aligned in the magnetic field. Whereas in case of the acetylenic, which is the triple bond aligns itself in this way. Okay, in which case the protons are a little bit shielded from the magnetic field. So that's why the double bond protons will come at a much downfield region than the acetylenic proton, the triple bond proton. Okay, so it's just a matter of how these things are aligning with the magnetic field. Then, of course, with the aldehyde, there is no question, all right, that you have the alignment that is going on just like the alkene bond, because there you have the double bond, and then you also have the oxygen in there, and so the proton really becomes highly deshielded. Regarding the alcohol and the amine signals, as I said to you, these 2 signals are quite different because they're not directly attached to carbon. All the other signals that we talk about for protons, almost all of them will be attached to carbons, but with alcohol and amine signals, they're attached to nitrogen. So they come slightly different. Their signal, the chemical shift in their signal depends on, the chemical shift depends on the concentration, okay, of the sample that you have, which means that you may see a little peak there, or maybe you may see a large peak in there, okay. Then there is also the case of hydrogen bonding going on, okay, in there. So, which means that the hydrogen bonding will deshield the protons. So the signals will be a little bit more deshielded. In some cases, what you can do is, in order to confirm that you actually have the OH and the NH, you will actually add a little deuterium to your sample, and if the peak disappears, then you know that that was the OH or the NH signal. Okay, so it's possible to figure that out, okay, using deuterium. So remember, we made deuterium solvents in order to have solvents that were NMR inactive, but you can do the same thing with alcohol and amine and exchange these protons with just deuterium. So you add a little bit of D2O, which is deuterium water, heavy water, to your sample, and it will exchange these hydrogens with deuterium, which means that in your original sample you will have a signal, but after deuterium addition you will not have that signal. So that is one way you can actually figure out whether you have protons, alcohol protons or amine protons or not, okay, because sometimes the peaks are not very clear. And then, of course, we have the carboxylic acid proton, which comes very, very, very downfield. Okay, and that is because of the oxygen here and the oxygen over here. So it's highly deshielded. This is the spectrum for acetic acid, and we just solved the problem. You will see 2 signals. One signal comes around 2 ppm, and again, this is because of the carbon over here, the carbonyl. And so instead of coming at around 0.9, which is where the methyl groups should come, but because of oxygen, it comes around 2 ppm. And then this proton, which is the alcohol proton, not the alcohol, but the carboxylic acid proton, that will come at around 2 ppm. Okay, the scale here goes from 0 to 10. In some cases, depending on your instrument, it can even go up to 12. Okay, but anyhow, that's what the spectrum would look like. So from this little presentation, I want you to understand the fundamentals of NMR, which means that how the NMR works, the nuclei flip, and what the scale is, the delta ppm, and how you actually calculate that. I may not give that to you in an exam, but at least you should know that it's a proportion, okay? And so you have the delta ppm scale, that's the fundamental of the NMR. You should also know about the equivalent and the non-equivalent protons. So I can give you a compound. You can tell me how many signals you will see. Understand the concept of shielding and deshielding. Okay, and so you should be able to predict the chemical shift also of different protons in there. So if I give you a compound which has 4 different protons in there, you should be able to tell me that this one will be the most deshielded and this one will be the most shielded and so on. Okay, so that's what I want you to take away from this little presentation. In the next one, we will talk about integration, we will talk about coupling and so on and so forth.